All right, so we've written out the governing mass balance equation for single phase flow here again. This is first order derivative of the mass accumulation term with respect to time. And this is second order derivative, right? First order derivative, second order derivative. So in 1D, it's going to be d2p dx squared. And the important point is that the equation features both derivatives. So we have to discretize both of them. And then I will show the different approaches we use to discretize the left-hand side and to discretize the right-hand side. And I should point out that the equation is continuous because we have partial derivatives, right? Whereas in the discrete form of the equation, you're going to be having delta x, delta y, delta z, delta t, all generally in the limits where it tends to 0. So small delta, small changes. The numerical methods typically solve discrete systems of equations. So we actually need to discretize this form of the equation, and then we can solve it. After we are done with the discretization, we will express the equation in matrix form. And that's when we can solve it using linear systems of equations. If the governing equation is nonlinear, then we linearize it using methods like the Newton or Newton-Raphson's method. So I already talked about this in class, and then I uploaded videos that go through all of this rigorously. But this is your Taylor series expansion around x plus delta x. And I want you all to go through these steps if you haven't done that already or you've forgotten some of these. And basically I work out all of these step by step in the videos from 30, 40, 56, which I've provided. So from these Taylor series, we can get the equation for first order derivative. We can get first order forward difference, first order backward difference, central difference, all from these expansions around x plus delta x and around x minus delta x. And you will also see the order of approximation of each of these derivatives. So here, the focus is on the time discretization schemes. And time discretization is also referred to as temporal discretization. You're differentiating anything with respect to time. And in our case, this is the mass accumulation term, which is phi rho for single phase. For multi-phase, it's phi rho s alpha. Of course, the rho is going to be rho alpha too. And so these are the options which we've derived from Taylor series expansion. This is forward because we are assuming it's forward because we are assuming that we are at n, right? And to find the derivative at n, we need pressure at n plus 1. For backward, we are at n still. And to find the derivative at n, we need the point before that. And then it's important to realize that the backward difference scheme we typically use, if we assume n plus 1 is the current time step, right? In reservoir simulation, that's a common notation. Some will use it in this form and say n is the current time step. But this is nomenclature I'll be using. P at n plus 1 is pressure at current time step, and then you need the value before that. So you're looking backwards. And this will give you an implicit scheme. This is what we use in fully implicit solution schemes. There is also the Crank-Nicholson, where we use some bits from current time step, some bit from the previous time step, which is shown here. And alpha could be 0.5 or any fractional number, but we're not going to be using this in reservoir simulation. There is also the adaptive implicit scheme, where we use the fully implicit scheme in areas where you expect the primary variables like pressure, saturation to be changing a lot, like near the wells, right? So you have a big reservoir this way, and say there are wells here, only 3 wells, and they are all to the east side of the reservoir. So you can use fully implicit scheme in all the grid blocks in this neighborhood. And then the grid blocks here, you use something like the implicit in pressure, explicit in saturation. So you solve for pressure implicitly, and then you do an explicit solve for saturation, or you use some lagging coefficients, some schemes that are not as expensive as the Newton scheme. That's basically what the adaptive implicit scheme is. Geometric interpretation, again, this is some review. In the videos from 4056, I've explained this. You're trying to find out the derivative at this point, which is pretty much this guy, right? That's what the correct value should be. That's the exact difference. If you use the backward, meaning in addition to the value of pressure at this point, you use the value of pressure at the preceding point, I minus 1. That will be backward difference. If you use this guy, right, this one, then you're using the point ahead of I, which is the current point. So that is forward. And lastly, if you use that slanted line there, you're using the points before, right, and after. Sorry, this is before, and this is, maybe before is not a good word. This is the previous point, right? This guy is the previous point, and this is the point that is forward with respect to I. And so it's central difference because you're using stuff before and after. Spatial discretization scheme. So remember I said for the accumulation term, we typically always use finite difference. Backward finite difference, first order, right? And it's also referred to as the backward Euler scheme, which we use for fully implicit methods. So regardless of whether you're using the finite difference method, finite volume method, or finite element methods, this accumulation term is always discretized the same way, and it's first order backward finite difference. But for the divergence of some constant multiplied by grad p, which is the second order derivative, you have these 3 options among others: finite difference, finite volume, finite element method. Finite volume method is sometimes referred to as the integrated finite difference method. That's the terminology used in TOEFL, but it's exactly the same as the finite volume method, which we will be talking about in this course. So these are some of the simulators that use finite difference. These are some of the simulators that use finite volume method. And this is one. I don't know if the company is still in business, but they use the finite element method. I think the company was bought, and then the name might have changed. Anyways, those are the 3 options, and these are their pros and cons. Finite difference method is basically an approximation of nodal derivatives. It's simple. That was the most commonly used back in the day, but it is limited to block structured meshes. The meshes don't have to be, the blocks don't have to be completely cubic or cuboid. They can be flexible, as you have in corner point gridding. So perfect example of that is what you see in Eclipse, right? You can use corner point grids. It also does not conserve mass locally within each cell. It also doesn't conserve flux locally at the interfaces of the grid blocks too. And that's why most software developers have moved on to finite volume methods. So Intersect is like the next generation of Eclipse, and that is based on the finite volume method. It uses an approximation of integrals. So you basically integrate the partial differential equations. It is mass conservative by construction, and it's suitable for use with unstructured grids. So grids that can have more than 4 sides. It's flexible in terms of the number of sides, and it can adapt to the discontinuities, right? Flow channels, fractures. You can adapt to those kinds of discontinuities within the reservoir. Finite element method is also flexible. It's based on a weighted residual form. We're not going to talk about this in this course because we're going to be focusing on MRST, which is based on the finite volume method. And that's the most commonly used approach for fluid flow in porous media today. It's very flexible, especially in terms of the gridding, typically using triangular grids. You can also use hexahedral or quadratic grids. It's suitable for use with unstructured meshes, and the standard finite element method actually does not conserve mass locally. What it conserves locally is actually energy. Well, there are some modifications to finite element method, like the mixed finite element method, discontinuous Galerkin finite element method, control volume finite element method, and these actually conserve mass locally.